Hi, this is Max. We've been trying to start this for an hour and 20 minutes. This is going to be our explanation of Lab 3 Shell project. So would you two fine gentlemen introduce yourself?
Sure. So, my name's Anthony. I'm about to be senior next fall. I've been a TA for CS252 for the past few semesters. Been a TA at Professor Gustavo since freshman year, so I feel right at home teaching this sort of thing. Not much else to say except my plans after graduating Purdue is going back to Purdue for a graduate program. So,
Nice.
yeah, hopefully systems or VR or something like that.
I'm Shri. I'm also going to be a senior. I've been TAing for a few semesters now for 252. I'm not an official TA during the summer. Instead, I'm a TA for 250, but I'm still dropping in to help out with talking about the Shell project.
At a certain point, you're never uninvolved with the going-ons of CS252, 250, all that.
As soon as you can join the cult of Gustavo, but you can't leave it. Can't leave it.
We forgot to write the destructor method.
Oh no.
That's an inside joke between me and Shri about a red-black tree project, but anyways, ready to start whenever you start.
Awesome.
Joining in my stream, Max.
Alright, you are in full screen mode. Go right ahead. Anthony's going to tell us a little bit about Lex and Yak, and then we'll be on to the project.
Alright, so this is actually all coming from a slide set I made a little over a year ago, spring 2019. This slide set was made as a bit of a primer on Lex and Yak to show you how to get to it. If you go to the lab sheet and then you scroll all the way to the bottom after all of the 20 pages is loaded, you'll notice that there's a resources section at the very bottom that has these slides in it. So after everything, this was something that was added in. This originally was given at a TA meeting, but Professor Gustavo decided it was good to have in there. And again, primary reason for making these is because Shell Project, while some might not think it's the hardest, it involves you learning a lot of new tools. And I thought there was a bit of a gap in having to learn Lex and Yak mostly on your own after a bit of explanation of like what the files looked like for shell.l and shell.y. So I decided to make this, and it has helped students in the past, so that's what I'm starting with today. So before going into what Lex and Yak is, another important thing is just why do we use them? Why do we have to do a grammar this way? Remembering the overall point of this project and what a shell is, we're just trying to create some kind of command line interface where the user can type in commands and interface with lower level processes just a lot easier. You know, calling ls, piping that into grep, you know, having that interface available for users is something that, you know, important to have. A lot easier than having to write some long, clunky, complex C file just to something that we can do in Bash nowadays. So in creating a parser to try and parse through and figure out what needs to be run, you have commands just like ls and pwd. It's really easy because you just have to figure out, okay, ls, that program is located here, pwd, that program is located here. Something like ls-al, a bit more complicated. You have to understand, all right, maybe I need to fit the commands into a program, but that's not too hard. Something like a bar, you might think, all right, first word is always going to be a command, and then once we hit a bar, we're going to restart with another command and arguments. But once you start considering that a user might want to type this just because they think the bar symbol looks cool, then you have to start keeping track of, am I in between two quotes? Has the user done something like escape the quote so I'm not actually out of quote mode yet? And especially things where you want to do for f in ls-al. Once you start getting into for loops and having to do subshell, or you may be more familiar with this syntax, it starts to get to be a bit too much to try and do this brute force. It's a lot nicer if we take a route called tokenization and syntax analysis, and that's what Lex and Yak do. So a bit of eye candy here on the right. Doesn't matter too much to look into and analyze all of its secrets, but Again, overview, we do our lexical analysis before our syntactical analysis, and the long story short of this is making sure that what the user typed in made sense. If they start an argument with the bar symbol, obviously we know that's not right. If they try to like direct output to 2 different files, we also know that that's not right. What Lex and Yak primarily are doing is it's helping us organize what we've got and make sure that this is something we can do with our grammar, that this is within the rules of our grammar. First step is lexical analysis. It's really important to understand that instead of dealing with the words ls, -al, pwd, a bar symbol, ampersand, what we're doing is we're turning these things into tokens. And that'll make sense going on, but instead of having to deal with, strings, what character values there are, what we're going to deal with, we're just dealing with things at a token level. Because when we have a bunch of tokens, it's really easy to do syntactical analysis to make sure, do all of the tokens fit together in a way our grammar expects. So to make a bit more sense of all of that, here on the left is Lex's job and here on the right is Yak's job. What Lex is going to do is it will take in a sentence such as, ls-al bar grep.cpp, and it'll start turning this into little tokens. If you looked into shell.l, you'll note that the file is the one that looks like this, where a certain pattern match returns a certain token. That's what's going on here. So this phrase here would go word, pipe, word, and then word. That's essentially what it would look like. So we start with this, we end up with something like that. And after Lex is done going through what was typed in, then we move over to the parsing tree with Yak and say, if we get something like word, pipe, word, is that something that we could actually do? Is that something that our grammar is capable of? And just in case you're a bit unfamiliar with the lingo, what we mean by grammar, what we mean is around the very top. You can also see this in the slides, where we have this sort of thing here, where we may have 0 or more arguments, you may have 0 or more things that come with pipes, you may or may not have that ampersand, you always have some sort of command, so on and so forth. That's what we mean by grammar, just quick clarification. With what Yak does, this likely, I'd say this is probably a point of good confusion for a few students the first time here in this lab, is just what is Yak trying to do with these tokens. Once it receives these tokens, after you've written your shell.y, the Yak will behave in a sort of top-down manner where it knows what it wants in the very end, and it's going to see if it can get there. At the very end, what we want is something, we're going to define in the file, we want a command list. Well, what is a command list? A command list has command list command line, or maybe it just has command line. So then what Yak will do is say, all right, it looks like I can have a command line as itself, and that would be valid. So if I want a command line, what does that entail? Well, a command line has all of these things. So you then can see the pattern here that when you see something that you don't know, basically something that's not a token, you have to look a bit further down and see, well, do I even have that? With pipe list, we look down and say, we can have pipe list, pipe, command, and args, or we can have command and args by itself. I'll explain what these italicized things mean in a second, but just bear with me. If we have a command and args, and that can be a pipe list, well, what does that mean? Well, we could have a command word and arg list, or just a command word. And then finally we get to the bottom where, okay, we have a word token. So that would be this word right here. After we've done our giant game of Plinko, command list needs a command line at least. That's going to need all these things. Well, starting from the left, we need a pipe list, which at least needs this, at least needs that. Okay, word. We found our word. Next, you'll see that we may also have an arg list, and an arg list is defined as arg list argument or just argument. And if we Plinko down just a bit, we notice that that could be a word token. So now these two words right here are now going to be known as command, word, and arg list. And we still have a pipe, a word, and a word after that. So we have our command and args, and this is where you can start to see the recursion of Yak. In our grammar, you see that we can have a command and then optionally as many arguments as we want, and we might not have any at all. That is explained by these pieces of the grammar down here. We could have a command word on its own. When it says in italics under or just this, that means, okay, we could have a command by itself because everything else here is optional. Or we could have a command word with an arg list that is now encompassing command word, and then optionally you can also have an argument list. We would want to symbolize things such as you can have pipe commanded arguments, pipe commanded arguments, pipe commanded arguments over and over again. That's where we're actually going to need a little bit of recursion, actually. So with this yellow box here, a pipe list could be defined as just a command and args. But let's say we have multiple things over and over. You know, let's say we have ls-al pipe grep.cpp. We will complete the first command and args as the ls-al, and once we start considering, all right, we built up the pipe list, is there a pipe? We realize that there is, and now after we realize that there's a pipe, we're going to check, okay, is there a command and args on the other end of this? And long story short, going through the same set of steps we did as above, we then figure out that we now have a pipe list. Everything here, we have word on the left side, the pipe, and word on the right side. Now, notice that these are the only ways a pipe list can be defined. A pipe list is a command and args, or it's multiple command and args together. It's like when it says the name of itself and then other things, it's like it can plug back into itself. So after the first command and args, that is a pipe list. It can plug back in, and then we can put another pipe and command and args next to it. But notice that we don't have just pipe list pipe. If we had our command just be ls-al pipe, we would go down, say, okay, command word is the ls. Okay, we also have more words, so that is also a word token. That's fine. We see the pipe. We're anticipating that there's at least something after that. So that is how Lex and Yak can tell that if we have ls-ar, al, and then the bar symbol, that's how we know that that is not part of our grammar. Because nowhere in here does it say you can have pipe list pipe, a command and args. That cannot be empty. That is defined as these bottom parts of the tree here. After that, it's pretty much just more or less the same thing. You may start to consider if you have the greater than sign, less than sign, what have you. You may have the ampersand or not, you know, saying that the ampersand, that can just be something by itself. And then you always end with a new line. This is important because when the user presses enter, that acts as a new line, and that's something we need to consume. It is important that you note that the direction of the arrows is top down as opposed to bottom up. When I first started learning this lab, I thought that it was bottom up, that it would take the tokens and then piece them together to get to the top of the pyramid, so to speak. But that leads to confusion, such as, you know, if you have a word token, should it start here? Should it start there? Should it start somewhere else? So that's why it's important to know that it starts at the top and it sort of trickles down. So talking about the .l file, shell.l specifically, Lex and Yak is encompassed in two files, shell.l and shell.y, and those two files are going to be the majority of what you're doing for part one of this lab. So with shell.l and shell.y, they're just part of a greater pipeline, which you can see with this diagram down here. This diagram goes definitely more in depth than you need to, but what you need to do about the shell.l and the shell.y is that you can actually treat them, some portions of them, similarly to a .c file. So it's possible that you can actually put functions and subroutines in there if you would like to. What a shell.l file looks like is you have a specific section at the top, 2 percentage signs, a specific section in the middle, 2 percentage signs, and then subroutines where you can put something like C functions, you know, if you like, and then you can call them from here, define them at the top, you know, all those sorts of things. This should be most familiar to you and probably the most readable part of this lab. is that in the shell.l file, as I was talking about above, first thing we got to do is we got to have tokens. We got to have all these tokens before we start doing this trickle-down method with Yak. So that's why if you see /n, we're going to tell Yak we found a new line. If you see this, we're going to tell Yak we found the greater than sign. What's interesting about shell.l is that you don't actually have to do anything. That is why you will see that there is a /t there. If used as a tab character, we need to consume that so we can move on to the next step, but we don't really care about that. We don't care about white space. That's why it's permitted to do ls tab-al tab bar, but if you do that, that's just uncomfy. So that's why we have to consume tab. We also have just a general regex to capture everything other than white space. And we do a bit of an interesting thing here, where before we return the word, we turn it into a string. I'll touch on that a bit later. But what's important to note is that you can have something called start conditions. You'll notice that as we run the grammar through here, we start in a top-down method. We are looking at each individual thing, and we're like, does this match the new line? No. Does this match this? No. Does this match this? Does this match this? Ah, okay. This much matches that bottom case, so we're going to return a word. And then it'll do that and realize the next thing can count as a word, and it goes to the pipe and it says, nah, not it, not it. And then if we had a match for the pipe, it would realize that there. But if you want to be pickier, and it's almost like you're adding if statements, such as if you encounter a quote, I want to flip a switch and put this in a certain mode so that only certain clauses can match. I'm just going to gloss over this because it isn't super important. You by no means need this for this lab. But if you wanted a bit of a fancier file, you may have a certain clause which is going to match $ open parentheses. This is a certain way that you can type subshell commands. Once you see a certain pattern, begin a certain mode, and then when you're in that mode, only a certain clause with a specific tag can catch. So like in this file, this was all there was. Only this thing be able to catch, and then you can put it back to normal, yada yada. If that sort of thing seems like that will be useful for you, you can definitely reach out to TAs, and we'll be able to explain a lot better. Tree knows them pretty well, so just to say that exists. Not super important though. You have the slides, you can go back to this if you need to. To move forward and talk about the Yak file now, this is shell.y, and it looks just about identical to shell.l, because you start out with a definition section, %%, then you have the main body of it, %%, and then you have whatever methods you want. So this looks just like the shell.l. Have definitions, whatever you want to do, and then subroutines. So with shell.l, you'll notice that this is filled in for you, but some of the definitions, we need to say what tokens we're getting from shell.l. So anything that we've said here, such as return new line, return great, return word, we got to put that at the top of shell.y. This is done for you, but an important thing to note is that word is actually a bit different. This is of type CPP string. Instead of just being a simple enum, we actually kind of care what the word is. To explain that a bit better, when we see something like /n, the greater than sign, we don't really care what the character value is. If you tell me it's a greater than sign, there's no other way I can interpret that. But if Lex were to just say, oh, I found a word, and then there was a word next to it, well, that leaves you wondering, what words did you find? Did you find ls-al, or did you find something different? So that is why we have to actually turn what we found into a string, and then we return the token. We will see a bit later that if you want to do some sort of string preprocessing, you can definitely do that in the .l file. Once this is turned into a string, we'll see a few examples of that later in the file. I think for the sake of time, I might even let you look over that yourself, but you can do C++ and C sort of things inside of Lex and Yak. Going back to the Yak file, all the tokens are there. After that, we start, with the subroutines function. If you feel the need that just to make your code cleaner, you want to be able to call functions at certain points, you can define all those functions at the very bottom. Just make sure they're past that percentage. And this is just unrestricted C++ code. Just whatever C++ code you want, you can put here. So it's just a C++ file. I don't know what to tell you. So the body of the .y file that comes between those two % signs, instead of like in shell.l where we were declaring tokens, this is now where we get the pieces of our grammar. And this will take a little bit of time to explain, but not by much. Let me see if I can actually clone this here. So this tree, is essentially represented by these functions in here. I believe, Max, can you still see that on your screen?
Yep. Still perfect view.
So, yeah. So it's like how we have this top-down method. We started a goal. What does that goal contain? A command list. We start with the goal, and what do we want? Something called commands. We then go, and we're like, all right, this is commands. What is in here? You could have command list, command line, or just command line. That's sort of like how we say we can have commands command, or just a singular one. Mine that down a bit further. A command can have all these things. It could just be like empty. It could just be one word. Be a word and then an arguments list, yada yada yada. You can also see the points where this is a bit recursive as well, where this commands here can actually rep into itself. So on the first pass, you might just catch the ls, and then later on you realize there's things after the ls that still could fit here, so the commands would just be ls, and then maybe this is a -a, and then later on this could be the ls-a, and then over here this could be a -l, something like that. This is just a bit of a further explanation of this, and also how if you didn't want to do any string processing in the .l file, you can also do it in the .y file. You can open up some curly braces, and you can just do whatever kind of function you'd like. At the bottom here, which I do recommend looking at if you're still a bit confused about it, this will definitely clear things up. I made a custom grammar where you do command 1, command 2, and then it's just like the stupidest grammar I could think of without giving up too much about the lab. But instead of something like ls-al barred into awk, you would do the two commands for the first thing, %, commands for the second thing. Silly grammar. I have no idea who would ever want to do it like this. I think there's even like holes in this logic too, where you can mess with this, but this shows an example of how you would want to write out this sort of a grammar, and this should definitely help, because this even goes into if you would like to call functions at the bottom, and I don't think I did start conditions in this, but yeah, start conditions would definitely have been overkill in this situation. But this is getting about to the end of my section, but definitely look at this example at the bottom here. This should, if anything I said was a bit outlandish, hard to believe, hard to understand, this should clear it up. But yeah, hats off to me about a year ago.
Very good. Let's go out of there. So next part here we're going to talk about is the actual... We're going to mostly skip over the Lex part of the lab now, because we talked about that already here. Yeah, that should show. So, look at the very basics of it. So the Lex part of the lab, all you're going to be doing, at least for this part 1 part, is expanding the grammar that it has. That includes changing shell.l to add more tokens, but also changing shell.y to increase that grammar and explain what those tokens do. So this is the current grammar your shell has. It can accept a command, it can take n number of arguments, and it can redirect output to a file. That's useful, but we want to make it do a lot more, obviously, so what we're going to let it do is, first of all, have a command with arguments, but also have any number of pipes with more commands and arguments. And then at the end, it can have any one of these redirects, 1 or 0 of them. They are defined later in the lab. And then we can also have an ampersand, and that ampersand is, of course, going to be to make something a background process. So these are some good examples to test with. I would definitely run those through, see how they do. But that first part of the lab is going to exclusively be making the lab able to accept those. Not even actually having it do anything necessarily, but just so it accepts those. And then we get to part B, part 1B, and this is where we're actually going to make things happen with it. So our building blocks of this part are going to be the fork command and the execvp command. These are two system calls, and they're going to let us create a new process that is running at the same point of code as the old process, and then execute some command with one of those processes. So Gustavo talked about this in lecture, I believe, already, but what's the basic idea of how any of these shells would work is you would call fork. Fork is going to give you is basically going to tell you either this is the child process or this is the parent process. If it's the parent process, you just either wait for the child to complete or don't do anything if it happens to be a background process. If it's the child process, then you're going to call this execvp, which we can look into real quick. So here's the man page for that. There's actually a bunch of different exec options here. Like execlp is used a lot. We're going to start with execvp. And it's just going to let you run a program, run one of the commands that's built into the operating system. That can be ls, that can be grep, any of those. So, and that, if there's no errors, happening, then that should never actually return. When it's finished, it'll just, that process will exit, which is just fine with us. The parent process will just keep going. So, yeah, we have the ampersand there. That's going to actually make it a background process, and will make it so we aren't waiting for the process to finish. And then let's go on to file redirection. So there's all sorts of file redirection, mostly because we have 2 different kinds of file direction we can do, and then 3 different channels that we might want to redirect. Well, two different modes of redirection and 3 different channels. So first of all, we might want to redirect standard output or standard input to and from a file. We might want to redirect standard error, like we see with this one. We might want to redirect both standard out and standard error. The other thing, though, we might want to redirect is do a redirection that appends to a file. So instead of doing a redirect where we are just overwriting everything we've put into a file, we're just going to slap everything onto the end of the file. This is particularly useful if you want to keep a running log of things that happens. And of course, the last option here is both. This is going to do an append with both standard out and standard error. Pipes are really good. So pipes, I'm sure you've messed with them in the shell lab, the shell scripting lab. What these are going to be is a way to communicate from one process to another. So what you're going to be doing with pipe is taking the output from one program. In this case, we can have ls, al. and feeding it in through standard input to another program, in this case grep. Now, normally pipes just communicate directly from one program to another, each through the same file descriptor, but we're going to have to change that because whatever program we're running here, in this case grep, we can't change it such that it reads from a different file descriptor. The program already exists and it's always going to read from standard input. That's fine though, because what we can do is use this dup2 here to make standard input, I can't speak, to make standard input point to something else. So in this case, what we would do is use dup2 to make standard input, instead of pointing to the actual standard input, that file descriptor, which for input I believe is 0, will instead point to the end of that pipe. Oh yeah, I did want to look at this real quick too. Pipe's kind of interesting because what it's going to end up doing is giving you a you're going to be giving it an array, and it's going to fill that array with 2 file descriptors. At that point, then you have those file descriptors are each going to be the ends of your pipe, whether it's the input side or the output side. Let's go back. And the last part of this, part 1 of the lab, is addy. Is_addy is going to be a function that tells you whether you're in the terminal or not. Basically, we just need to make it such that we don't print a prompt when we're not in a terminal. So if we end up writing to a file or something, if we're doing a file redirect, then instead of printing our prompt inside the file, we print it inside. We don't print it or wait until it's in the terminal. And that's mostly for testing, because a lot of our tests won't really work well unless is_addy is working. That part should be pretty easy though. It's basically just throwing in this function into your shell. So that's part 1. Part 1 is definitely, it can be rocky to start with, especially because Lex and Yak can be difficult to understand. Definitely go over Anthony's part again if you still don't get it, or take a look at the slides. But it shouldn't be too much work once you understand what's going on with it.
Number 1 TA quote of all eternity. Aside from, it's not that bad, it's easy once you get it.
I still need that t-shirt. I still need to make that t-shirt.
I'd buy one.
Yeah.
Alright, so part 2, Control-C. Basically, normally when you're in a shell program, you type Control-C, everything stops, which is exactly what you want. But you don't want that actually in your shell. Because then, first of all, it's confusing, and second of all, you don't really need it to. You can just type exit. Hopefully your shell isn't breaking enough ever that you would need to do a Control-C to it. So
you also would. Oh, sorry. Just add. You also wouldn't want a Control-C meant for a running program to kill the entire shell. That's like trying to turn the lights off and all of a sudden the whole ship is going down.
Yeah. That's turning your lights off with an EMP. It's just unnecessary.
That's a great way to put it.
So you're gonna to do that. Basically, we want to make it ignore Control-Cs, and we're going to do that with this sig_action function here. We'll take a look at the code in a little bit, and you'll get to see a little bit more of how we do that. It's pretty easy though. It's just using using sig_action and using some structs that come along with it. The other thing that we're going to need sig_action for though is the zombie elimination. if you have background processes, they don't just disappear when they're done, unfortunately. They're waiting for the parent process to give it the okay. So what we need to do is basically have this callback set up in place with SIG_action that when the process ends and it asks the parent process, hey, can I stop existing now? It just says yes. And that's what this part is. We're going to catch these SIG child signals, and we're going to make it send back a response that will let it exit. And you can also then print out that it exited, which is helpful to the user. Another quick little one we can put into the shell is exit. Let's let the person exit the shell, especially if you just implemented Control-C. You should probably implement exit too, because then you can actually leave your program without a greater amount of pain. So yeah, exit's just going to kill the whole thing and do a little message saying that it's leaving, so a little goodbye message if you want. And then we get to quotes. Quotes are fun. Quotes are going to make white space not count, basically. So we can have one single argument that takes up multiple words. In this case, we have ls command.cc space makefile. And instead of, basically what we're doing there then is saying, instead of having ls and then this argument and then this argument, we're treating this entire thing as one big argument. Importantly, though, when we pass it as one big argument, we have to actually get rid of those quotation marks because the program that we're sending it to is not expecting quotation marks. So we have to make sure to do that using, I think usually we do that in Lex, not Yak, correct? In the past, I've always done it in Lex. Am I correct there?
Doing which part specifically?
The quotes.
Quotes, I think the official, like, Professor Gustavo response is usually to do it actually in simple command .cc or hh or c and h where like you track the quotes separately. But yeah, you can also do it in Lex. Yeah. I did start conditions, so I obviously did it in Lex. I just have like a quotation mode that you can read. Doing it in Yak, I've not really seen.
Yeah,
usually people either do it in Lex or do it in simple command, like tracking separately.
It would be a pain to do it in Yak, but yeah, you can use it in Lex and then I would suggest doing it in Lex and then extracting everything between the quotation marks. However, with quotation marks comes the need for escaping things. So let's say you want to have a quotation mark given in your input. In that case, you can put these backspaces in, and that should be able to nullify that as a part of the quotations. So.
Oh wait, actually, yeah. The official response. Sorry, I got it mixed up.
Go ahead.
The official response that Gustavo was saying is quotes you do in Lex, like you have a separate regex for that, and for stuff like environment variables and maybe like auxiliary stuff you can do in simple command. But yeah, quotes are supposed to be in Lex. My bad.
Cool. Just making sure. So like in this case though, we have these escaped quotation marks. So this is not one giant argument here. It's actually going to be 3 different arguments. And those arguments are going to include the quotation marks. So we're not going to be getting rid of these because they're escaped. We are going to be getting rid of the actual backslashes though. And again, that's different from up here because the command that, or the argument that we end up passing it is going to be this, not including the quotation marks. In this case, the argument we're passing it is this, except without that. And yeah, that can also be used when we're not even talking about quotations, such as if we want to have an ampersand at the end, but we don't want it to be a background process. That's also going to be used to escape those as well. It's basically going to escape any special character. Next, we're going to make some built-in commands. So a lot of commands that you get in a shell aren't actually commands that were put onto Linux and were written out as an actual separate program. It's just it's meant to act like that, but it's otherwise a command that's built into the shell itself. So we have a few of those that you need to make. Print environment, that's going to print all the environmental variables. Environmental variables are their own little beast, but the important thing is they are stored within this char star star environ, and that's going to be a null terminated array of strings. You can look up more about that on the man page, but that you're going to be doing a lot with for most of these built-ins. We have setEnv, that's going to be setting the environment, setting an environment variable. The first argument is going to be the name of the variable, and the second is going to be the value that you're giving it, a string, of course. UnsetA, that's going to be the opposite, saying I'd like to take this out of the environment. Source is an interesting one. In source, we're going to take the file that we give it. It's always going to be a file in this case. And we're going to go through it one line at a time and run it. So this is going to be basically running your shell scripts. You can learn a little bit more about that and using multiple input buffers here, but it's basically it's source. It's running a shell script. And lastly, CD, change directory. That's pretty simple because you can just use the change dir command here. But there's kind of an unspoken thing throughout these built-ins, and that's, are we treating these as a separate process, or are we treating these as the same process? And it's not the same for all of them. For example, if it's giving output, we want to treat it as if it's its own process. We're going to still use our fork command, and we're still going to run it in there. We're just not going to use execvp with it, but we are going to fork a new process. Printenv is an example, because we might want to take that environment that we print and run it through grep or something like that. And if we're doing that, we are going to need to make it its own process. However, if we do something like change directory, we need it to be the process that we're on because we're changing the directory of the process that we're running. So we don't want to create a new process for that. We want to run that outside of a fork. So that's just something to think about when you're implementing these is, where do I put it? Do I put it inside the fork or outside the fork? And if you aren't quite sure, you can ask on Piazza, or better yet, go to the test cases. You can still read all of them and see what it's expecting from those. Another important little feature to add. We can start the user out with a .shellrc file. It's going to be like bashrc, and as soon as our program starts, it's going to act as if it just did the source .shellrc command. So that's where you can put things like setting up environments and stuff with that. Next, we have subshells. And subshells, I think this is kind of this is the biggest part of the second part of the lab. This is the it's larger piece of code, and we talked about subshells a little on the video on shell scripting, but the basic idea is we want to run a program outside, take its output, and put it back into our buffer here so that we can use its output in another program. In this case, we might want to use the expr command to do some addition in this case, and then whatever that output is, replace this entire block with it so echo can finally output 2. And the way we're going to do that is fairly straightforward. We're going to take our shell that we already have, and we're going to run another process of it, and we're going to give it as input whatever was inside of either our backticks or our $ parentheses, and it's going to run that, and then we're going to put that back into our buffer so we can use it again. And this is a nice little chart showing how that works. So here's the algorithm for that, really. We're going to take a command containing a shell command or a subshell command, and we're going to put it into our buffer here. So we have our input buffer that has echo, in this case $ parentheses ls, and then this and more string. So what we want it to do is print out all the files and then and more at the end. Next, we're going to parse that echo command. Makes sense. We now know that our first command in here is echo. Then we're going to get to the $ls, or backticks ls. At that point, we know that we need to do some sort of subshell stuff. So what we're going to do is execute that command in the subshell. We're going to take ls, run it in a subshell, and whatever that output is, we are going to put it back into the buffer here. And the final thing we're going to end up with is a command word that is echo, and our arguments filled out as file1, file2, file3, and finally the and more one. The way you're going to have to do this, though, is you're going to have to look for it, obviously, in shell.l. You're going to have to call your own shell as a child process and communicate with it via pipes. A lot of people, what they do is they'll take the pipes and they'll actually redirect standard input and standard output. That is fine, you can do that. The other option, though, is you can actually just read and write directly to those using the read and write functions. And that's probably going to be easier. Once you finally have that output, though, you can go ahead and use YY_unput, this function here, to add those back in. Make sure to do it in reverse order, because otherwise it's just going to end up being reversed, mangled. Treat it like a stack, basically. And at that point, you've added it back in, and it can continue parsing just as it was before. And yeah, that's it for subshells. It's not a super complicated idea, but it can be a little bit of a pain to implement. It's definitely very useful, though, because you can do a lot more when you have access to subshells, and you can use output of programs within other programs, basically. We have a very similar concept here to process substitution. This is extra credit, as you can see by the green. Basically, the way this works is if you want to treat the subshell kind of like a file instead of a process that's running, it'll do that. We're not going to get too into this because it's extra credit, but the basic idea is it's using something called named pipes. Make FIFO and everything like that. Make named pipes are the main thing though, and we can do stuff like running this echo hello and then sending it over to Vim so that we can edit it in Vim. And that's it for part 2. Part 2 is a lot of little things mostly, and then subshell's the bigger thing. It's definitely gets into a lot of the meat of making a shell though. So now we're going to move on to part 3. Part 3 starts off with environment variable expansion. So we've already done some environment variable things up to that point, usually mainly with the built-ins. What we haven't done is actually made it so that you can access those easily within a command. So what we're going to let you do is whenever somebody puts a $, curly bracer, and then the name of whatever environmental variable, it's going to expand that to be the value of the variable. In this case, $A is going to be made into being hello, and B is going to be made into world. And these aren't necessarily like white space dependent, so you have to be ready to have multiple of these in one word, or having 2 of them, in this case 2 in a word, and then you can have other letters in between or not. Basically, you need to be able to work this into your normal word processing in a lot of ways. The way you should probably do that is mostly with C. I would, you're going to have part of that in your .l file to actually go through it, but mostly I suggest using C functions to handle a lot of that, because it's going to be a lot easier. And then we want you to add a few of these special variables that aren't going to actually be stored in the environ, but if the user asks for them, you're going to supply them. They track a number of different things. You can mostly keep them just by having some global variables that you keep track of. But yeah, they're good to have. Next is tilde expansion. Basically, the user has a home directory. We want to be able to tell them where that home directory is, so tilde is just going to expand into being that home directory. With that, I'm going to hand this over to Sri, and he's going to talk to you through wildcarding and the edit mode, the line editor. So let's...
Alright, I believe I have my windows set up appropriately. I think I should... can I just share everything?
Yep.
Yeah, okay, so hopefully you guys can see this.
Yep, looks good.
Yep.
Alright. So before I get into wildcarding, I thought I should make a quick note of, if you go to the site, okay, for some reason it's looking like this right now. If you go to the book link, there it'll take you to this page, and here is when the professor is writing a textbook for this course. He has a section for the shell. So this is one of the labs that is featured in the book. I don't think all of them are.
You should definitely look at that book, though, because it has a lot of the lab in it.
Yeah, it goes over... this is already stuff that Anthony's talked about. It goes over Lexiac, a bit of the command structure. Also, the slides are helpful. I'll be showing a bit of that, too, if I need to. I'd also like to point out this quote, which is absolutely one of my favorite quotes from the man himself. So with that, moving on down to wildcarding, which
Real quick, just to point out, just general resources at the top of the lab sheet. If you want to go to the tab real quick, there's a bit of a hidden resource there. Like how at the very bottom there's the Lex and Yak slides. There's the FAQ and additional notes that will probably help you a lot with zombie processes. Just want to put that out while we were pointing stuff out.
Yeah. Please check these out too.
Go to every resource you can in this lab, because if you do, you'll find a lot of little hidden gems that'll make your life 100 times easier.
Definitely. All right. So yeah, this is talking about the command structure, and my Wi-Fi is. Oh no, I don't think that's my Wi-Fi. I think that's just my old computer. That time it was. Okay. Still scrolling. All right. So here's the section on wildcards. So the book does a really good job of explaining this. I'll be taking a look at it at a more conceptual level, because this does handle a lot of the code. Basically, the first step is yep, I'm where I need to be. So the first step is that right now in your Yak file, you basically are just looking for any time that you see an argument. Actually, you know what? Okay, hold on. Let me introduce what wildcards are first, and then I'll jump back into what I was saying before. So a wildcard is anything that allows you to get multiple files or things that are in a directory. So for example, if I want to cat one file, okay, well, we'll do that one. I know that's a short file, right? So that's great. If I want to cat every C file, I would do something like this, right? Or maybe let's say like ls every C file. So that gives me a list of only the C files, right? If I just want to get like one file, you can do that. ls, if it takes an argument, it just gives you that specific file name. But the point is that wildcards are kind of this selective thing. Here it's looking for any set of characters followed by the letter C. If I wanted like only files that had CC, I could do something like this and only get the CC files. This can be used recursively across multiple directories. So let's go back to, okay, so this is like my home directory on data. Let's say I want to look at all of the files across all of the classes that I've taken that have like C files in them or something. That's a lot. But so basically what that wildcard was is asterisk is any series of characters, and question mark is a single character. So if I replace like this should give me H files too, because question mark is a single character. There's also some .o files. That's a lot. Wow, I've been here a long time. So that's the basics of wildcards. The idea is that, as you can see, that it can select any directory name. It's not something that just happens on this last selection here. It recursively goes through and finds any directory that fits this one. Then within those looks for anything here and looks for anything there. So these will be like your lab 4, lab 5 source directories for like CS252, CS251, yada yada yada. Notice how, because of these question marks, it never looked in this folder here, for example, CS252 underscore spring 20, because this is only looking for 3 characters. So, I mean, these 3 characters happen to be numbers, but I want to make that clear. It could be any 3 characters. But it doesn't have to be. If you're using like asterisk, it can be any number of any characters. There's some more nuances in there, but that's basically all you need to know for wildcards on a functional level. So let me head on back to where I was before. 3. So the textbook walks you through gaining this sort of functionality here, or that, where it only works in the current directory. And so the way you start that out is, now I can go ahead and vim shell.y. No. There we go. No, that's not what I wanted. Okay. Here we, for argument word, this is just a print statement, and we're inserting the word that we received as an argument into our simple command object. You'll understand more of this if you take some look into the source code. This is just the objects. This is just some object-oriented stuff to handle how we're tracking our different commands in our command list, etc., etc. Max already talked a lot about that. So right now we're just inserting this argument. The first step is to change that into calling this expand wildcards if necessary function. Now that doesn't exist yet. You'll need to implement that, and you can implement that right here in the .y file. As Anthony said, you can treat the .l and .y file as kind of extensions of C or C++ files as long as you import the correct libraries up top. And so essentially you want to change this into expand wildcards if necessary. And we pretty much do give you the entirety of the code for this logic here. I think this textbook specifically, yeah, so it's got some weird Unicode stuff going on there. So I think I'll take a look at the slides if they decide to load today. Oh no. Okay, there we go. Man, I had all this set up and then I changed window sizes and it all went away. Yeah, so here it's talking about that. And after I cover this, I will explain how to handle like the recursive wildcarding. But it's important to understand this is an important first step just to make sure that you learning how to do this stuff understands how this works.
Yeah, you should definitely start by implementing one level wildcarding and then get to the recursive stuff.
Yeah, I'll talk about how to translate the logic for the first level into how to do it recursively. There is going to be, you won't be using everything here literally, but a lot of what you learn will be important. So I'm not going to explain too much about how this works on a code level. I think the comments do a decent enough job. Instead, I'm going to make a notes.txt and just show you guys more conceptually. So let's say the command that we're looking at is ls.c, and then we'll do a question mark. So that way it can either be, actually, you know what? Let me double check this. If I do, there we go. Okay, we'll do asterisk dot question mark. So that gives me C's, H's, which there aren't any, L, Y. Or we could do that, which will get me CC and HH. Doesn't really matter. This is just an example. We'll do that for now. Yeah, what the hell. So you know, this first, when Lex and Yak are going through ls, it's just a word, good to go, right? We run expand wildcards if necessary, right? Because we changed it. Oh man, this is so slow. I'm sorry. Right, we changed it. So we run expand wildcards if necessary on this word. Oh, well, it's not an argument, so we don't. Yeah, so this is just a command word, so we're fine. And then this is an argument. So we'll do expand wildcards if necessary. Let's check to see if there's any wildcards. Of course there is. We see both an asterisk and a question mark, so that's this bit here. And so we're not going to just insert it because we actually want the content that's there. We want to expand the wildcard. So to do that, there's a few steps. You guys may have learned a bit of regex in 251. The basic rundown that I can give you is that regex is like a series of rules for a series of characters to qualify. So it's a way to identify specific expressions or characters. That really was not a good explanation, but the idea is that you can match certain words that either fit a regular expression or don't, right? So, you know, going off of our example here, this fits that this fits that wildcard. That's not a regular expression. This does not, because question mark, single character. This is 2 after the dot, so that's not what we're looking for. Our first step that we're doing here, this is C code. You guys can do this with C++, and it's a lot easier. You don't need to worry about malloc-ing and stuff. The first step is that you translate this into regex. And so wildcarding, the notation is asterisk is any series of characters, question mark is any single character. Regex does it differently. Regex has regex does dot for any single character that isn't white space or something, and then asterisk repeats the previous thing. So we want any character any number of times, right? And then we want an actual dot, and so we skip, because regex, like the period is an actual like key character for regex, like it signifies something, right? Any character. So if we want an actual dot like we do here, then we have to escape it. That's what this comment's saying, I think. And then we have one question mark. And so again, we do dot because wildcarding one question mark means any single character in regex is just a dot. So now we have a regular expression.
Oh, we also have to add the $sign at the end and the caret at the beginning, but yeah.
Yeah, good catch.
Other way around.
So this is just, whoops. My regex, every time that I talk about regex, it takes me like a few minutes to relearn it because I don't use it all too often, admittedly. But yeah, so this is start of regular expression. This is a regular expression. This is end. So if there's a file that has this part in it, but not entirely, right? So if we had I don't know, like Java, right? So it has, like, if you just look at command.j, that does fit this, but there's stuff after it. And this $sign over here prevents us from matching it because it has stuff after it. So sure, part of it fits, but we're looking for a start, a match, and an end. So this does not, this would not pass. Our next step is just like some library interfacing with the regex library that we're using. You guys can check out this example here. I don't know if it's my source. It might be. I'm not going to check right now. But the idea is that you compile this new string that you've generated, right? These are like C strings or whatever. I'm not going to put quotes that don't make it confusing, but this is like a C string from, the argument. This is your C string for the actual regex. You do regex comp, which is compiles it into a regex object, and you make sure that it works, and then you run it on your directory. You're going to use opendir here, which is like a system library. Pretty cool. And then you're going to read through your directory and then check to see if the regex matches. I know I said I'd be talking about conceptually, yet here I am literally explaining the code. That's okay. So let's say in our directory, I mean, you saw my directory earlier. I'm not going to get into it. There's, command.c, command.h, shell.l, shell.y, shell.h. No, that's shell.h. There's a bunch of stuff. And some of them match and some of them don't. The ones that do match, you insert as an argument, as you would normally. And for the ones that don't match, you don't insert. You just move on. And then you close the directory at your end. One thing to note before I get into the recursive stuff with wildcarding is that this example in and of itself is also kind of superficial. Typically, wildcarding, and I think the test cases reflect this, want alphabetical wildcarding. So I would say here, instead of inserting into an argument, you have some sort of like global, you have some global list of strings. C++, again, this is like really easy. Otherwise, it gets kind of annoying with malloc. But if you want to do that way, perfectly fine. You could put all of those into this like vector or list vector of strings, and then here, right before you close out of the function, like you close the directory, you sort that list, and then you go through the list and insert the arguments. That way you get your alphabetical order. Another thing to note, and I'll reiterate this towards the end, is that when you're inserting these arguments, notice how that you're doing str dupe. This uses malloc. There's some test cases or some grading that involves checking for like memory leaks and stuff. These are strings that you're going to need to free after you've handled the command. And depending on the specifics of your implementation, if you're like duping like multiple times, you may need to free in multiple places. So just keep that in mind as we move forward. Yeah, so here's sorting directories, right? It'll give you sorted, so you'll need to alphabetize as you go forward. Yeah, so this bit goes into how to use an array and sort it properly. This is a C implementation. You can bypass a lot of this, again, by using C++. There's going to be the web server lab is in C++, so if you guys are looking to get C++ experience, this is the place to kind of do it, because it does objectively, I think, make your lives easier. This is a bit about hidden files. I won't stop on this too long. Basically, let me get out of here. Hello. So I've got some hidden files here. I've got some .gits, and then of course this is just current directory and parent directory. Notice how echo asterisk does not get those. That's because that's just the way wildcarding works. That's the notation that's been chosen, that if you're just doing this, you don't get hidden files. If you want hidden files, you got to do something like this. And then you only get your hidden files. See, if you want a file name that starts with a dot, you got to add it at the beginning. So just a special check for that, right? If a regex matches, just make sure that it doesn't start with a dot, because technically speaking, right, .git does follow the asterisk rule that, any number of characters, any number of times, .git ignore .git follows that. So we add this extra check. Sure, you follow our wildcard, but we don't want hidden files, so we're not going to add you to the argument. Or rather, yeah, I think that's what it is. But yeah, that's just hidden file stuff. You can read that over. The test cases do make sure you handle that, so if you're worried about that, take a look at the test cases. Now we get into subdirectory, and this uses everyone's favorite concept, recursion. I like recursion. I think that I understand it decently well. And characteristically, what that means is that it's usually not efficient programming, but it's efficient here. So we'll go back to our notes. So our example here is this. I'm not really sure I like that one. I'll do a different one. So let's say I'm looking for, what was the one I had? I had CS, question, anything. Let's get fancy. Anything, and then...
That's fancy, all right.
Any C file. So this way I only get... Ooh, you know what? There you go. How do you like that?
I'm shocked and astonished.
Big brain moments. Yeah. So let's say I want to show someone how many C files I've written in all of my classes, right? So CS. This should be CS followed by three numbers or three numbers or letters if you're somehow taking a class that has that. Lab followed by... Okay, we'll do this. Maybe there's some labs that are... maybe you're taking a class that has in the double digits number of labs. I feel sorry for you.
Ooh, lab 25.
And then... lab 99. And then... just looking for the C file, right? So pretty standard stuff. So this is going to use concepts from what I just talked about with like current directory wildcarding, but keep in mind that you can't just kind of copy paste all of that code and use it here. You're going to need to really understand what your code is actually doing for the previous code that I just showed you. to then implement the recursive portion of it. I'm going to talk about it conceptually, and then I'll give maybe some tips on the coding part of it. The idea is that you receive this string here, right? For this, I'm gonna be skipping translating into regex because that's just gonna take up time. And by this point, I hope this example kind of covers how the regex operates. So you have this string here. You have a current string and I think the way the code does it is just has a prefix and a postfix. So postfix is anything that has yet to be kind of parsed and looked at, and prefix right now will be nothing. Prefix is what you've already looked at. This is recursion, so let's say we're over here, right? In this specific, in the function call that is handling this wildcard, this is the prefix. Okay, I can't have /user/lib is the prefix, and a star is the postfix, because this has already been handled. Okay, and now's a good time as any to make a quick point. The idea here with this recursion is that you want to create this function that takes in a prefix and a postfix, handles the wildcarding for the current directory, and then that passes it on to another function to handle the next prefix and postfix. And that function that you pass on to is the same function. That's how recursion works, right? You keep passing it on to yourself in different states. So you have a function here that handles this, and it'll take care of this u star and pass it off to itself with a new prefix and postfix to handle this bit, and that'll pass it off to itself and so on. So your goal is to say, all right, I'm in this directory, let me just handle this wildcard and leave the next iteration, the next wildcarding to the next iteration. That's what's going on here. So this is our prefix for the current iteration of this wildcarding strategy. So we'll do our regex on this. We'll get all the valid files and directories. So let's say these are what we've got, right? That's non-numerical, whatever. Let's say there's also a file that for some reason isn't named this. Just bear with me on this one. Oh, whoops, I forgot a slash here. I'll get to this case. So we'll say this is a file and these are directories. Great, right? So for this, this matches, right? So we will call another iteration using CS252 as our prefix, and our postfix is the rest of our string here. And so let's say, one step that I guess I did kind of skip over. You need to have some code here that looks at this and extracts up until the first /, right? Because you can't analyze all of this for the current directory. The only thing that matters for this current directory is lab star-source. So you got to have, again, the C++ string libraries, really good for searching. Obviously, C libraries have good string searching as well. So you should be able to do this no problem. So we are only looking at this bit here. If it helps, I know that Anthony did it this way. I'm not doing it this way because the code in the slides isn't reflected, but it's totally within your bounds to have a third argument for current, and then that way, just for peace of mind, you can have this be your current, and then this just be your post. So that way, there's no confusion. But I'm going to leave it like this because that's the way the slides kind of go for it.
Yeah, as a quick clarification, the reason I identify it like that is because the very first thing you do is you split the suffix into two halves. So I just thought it was more straightforward like that.
Yeah,
just to show there's more ways than one to do.
Yeah, 100% agree there. Yeah, so first thing that you do is extract this bit, and then you're going to be checking all the current files and directories against this wildcard. Again, you translate to regex first. Not going to do that. Let's say we get lab 1, lab 2, and lab 3. And let's say lab 4 is, for some reason, let's say, you know what, I'm already handling that case here. So we'll just say this is all directories. This is already files, so I'll get to talk about that at the end. So for now, lab 1 source. So now we're here. We've made a call recursively to our expand wildcard function here, where our prefix is now CS/252/lab1 source slash. And I like to, I think having the slash at the end of the prefix is better, because otherwise, if you're trying to search for directories like this, you're not going to find any files. So this is now our postfix, and then we'll say main.c util.c, and let's say that there's bear with me on this one. Let's say that there is a it's really stalling right now. Okay, let's say that there is a directory called dir.c. I know that it says it's .c. Let's just act like it's a directory just for this example, and I'll get to that. So main.c, it's a file. This is our last postfix. There's no slash. There's nothing else. And so the way we kind of handle that, we found something of value, is we would make another recursive call where we get, we take our result and we append it to our prefix, right? And then our postfix, we just remove what we were just looking at. Perfect. Right? Just kind of continuing with the quote dumb recursive logic. And then our postfix is nothing, right? And then so we see that in our final iteration, we see that we have a empty postfix, and we say, okay, that means we succeeded in what we were looking for. And then we would go ahead and add this to our vector of strings or whatever to then sort and insert at the end of all of this. So again, how we know that we've reached the final iteration is when our postfix is done. That'll be the same for util. You're like, I found util.c, and it's a file, and I'm not looking for anything further. So we go ahead and add that here as another iteration, just a recursive call. Anything that comes up, we call again by adding it to the prefix and removing it from the postfix. You can see that through these whole iterations. As I continue, hopefully you guys start to see the pattern, if it's a bit confusing right now. And so again, we see our postfix is empty in this iteration, so we just add it to our array, we're done. Here's a directory. Whoops, that was page down. God dang it. I'm framing out so hard that I can't tell when I'm doing something right and not. Okay, so this is dir.c. We'll say it's a directory, and I know it's the .c file. I didn't think this example through. Sue me. Dir.c. So this matches, even though it's a directory, it works, and so we take it. The reason that I have this is, let's say our postfix, let's say our wildcard in the beginning had like had a slash, right? Like if there's a slash here, then we would see this is a file. There's a slash at the end here, meaning like that we still got work to do, potentially, right? And this is a file. We can't open it as a directory. Like you can try running open dir or whatever, and it won't work. And you'll be like, okay, I can't move on with this, and you won't even call another iteration. That's the idea here. And so dir.c would pass this specific postfix because like it matches here, and like we see that there's more work to be done, and we see that because this is a directory, we can do more work on it. But this as a directory also passes this because like what if this is all we're looking for, right? Even if it's a directory, it doesn't matter because we don't care about opening it to look recursively. So this would also work. I'm not going to type out the prefix and postfix for this recursive example, but it works. And then so that was all of lab 1's source. Continuing on to our list from when we checked CS252, we also have these other labs, and this is going to continue down the same line. Let's say you've got your main.c, helper.c, and you run, you extract your regex, or you extract this regex, you run it, you check it, you go into the next iteration, so on and so forth. This happens for CS250, CS251, yada, yada, yada. So let's say CS251 went all the way down to like CS251/lab3 source / string.c. Maybe you have to implement your own string.c for lab 3. I don't know. And so that works. And then to travel all the way back up, think about it as, I guess travel's not the right word, but so this guy made all of these different calls, and so you finished this second to last call. You finished the second to last thing in the original list for this wildcard. And now we have the CS252, which I said, bear with me, is an example of some file. And so this is kind of the inverse of what I was talking about here, where at this point in time, I'm just going to type it again to avoid confusion. By this point, we don't have a prefix, and our postfix is this. And so this was our extracted wildcard. We changed it into a regex. This matches. However, we see that there's a slash followed by more stuff. And because this is a file, we can check that it's a directory by, again, running opendir, or there's some is directory, or there's a bunch of system library functions that you can look at that I'm sure are listed here. There's many ways to do it. I don't want to endorse a specific one. To check if it's a directory or not. This isn't a directory. We see that we have more recursion to do, so we will not be continuing forward with this one. If you watch Shark Tank, this is a "for that reason I am out" moment, and that completes the example here for how recursive wildcarding sort of works. As you can see, the main point of contention here, if you guys are really looking to kind of use what you implemented previously, trying to add as little code as possible, I understand. You're going to need to change the function definition here to take in these 2 arguments, or maybe 3. These would be C++ strings or C strings. And the page is unresponsive. Let's give it up for my ThinkPad T430 from 8 years ago, and Google Chrome for having the gall to do this to me. Okay, so I can't scroll anymore. That's fine. I'm a professional. The point of contention is in.
Quick question: do you want me to try and find this for you, and we're streaming me while you talk? I can do that in the background. Continue, either case.
Okay, I'm just gonna reload the darn page. Screw you, Chrome. But it's gonna load all of these slides.
Was there any more on that slide set that you needed for that?
No, I mean, the main thing that I wanted to point out was in the original expand wildcards for when it was just current directory stuff, there was a point where you decided to add it as an argument, after you check that it matches the regex and all of these different things, you add it to the argument list, and then I said replace that with adding it to a vector, so at the end you can sort it. Oh my god. Get out of here. Oh, this didn't crash. Okay, we can use this. So here, right, this is just for the current directory. There's this point where you realize, okay, this matches the regex, all good, and you insert it in. And then I said, instead, change that to adding to a vector, and then sorting the vector here. So that's all well and good for the current. There's going to be some elements of basically changing this to be a recursive call on another iteration of this expand wildcards function. Or expand wildcards if necessary. I would also consider having, even here, having this sort of intermediate step where I would say it is actually my recommendation that you check if you need to expand wildcards here beforehand, or you have a separate function for it. Man, I think the slides show that in the revamped version you have expand wildcards if necessary that just does this. And if it doesn't, then it calls a recursive. There's a function called expand wildcards, and it just calls that. And so this function is only this long, and then expand wildcards is all of this. And the point here is that you might need some other intermediary functions, because you only need to sort the arguments list once. and that's up here for expand wildcards if necessary. And then so here you would call you would call your expand wildcards function, and then sort the list and everything. Down here, instead of inserting argument, you would kind of recursively call it, and then if you find something that matches, you would add it to the list. You make sure you close all your directories. You need to make sure that, like, when you're string duping, that you're doing it correctly, and that you're freeing everything that needs to be freed. I think that's it for wildcarding, though. I know that last bit is rushed. These slides are going to take a long time to load. But yeah, that was the final point. Hopefully this example really gets you going. I strongly recommend make sure you just get the current directory version working. You'll pass like one test case and that's fine. Second piece of advice, don't get too hung up on having to reuse all of this. Like save this code when you run it, like comment it out or whatever, make a new function and start writing that using this as a reference. Avoid getting obsessed with like saving all of this code. This is more important as an understanding step than a physical. I typed out the code that does this functionality step. There will be reuse. So if you really know what you're doing, you can just copy whatever you need over. But like really make sure you understand where this is working and how it's working, and how this example translated into recursive code here. I believe there's some recursive code in the slides. At least pseudocode or something like that. And I think that is it for wildcarding. So I'm going to move on to T2Y now. T2Y, fun note, actually stands for talk to you later. Or that's T2YL.
That's TTYL.
No, but that T2YL is an actual systems thing. Like they actually, that T2YL is a device that is on your computer.
The only difference is that I'm not gonna talk to you later. I wish I wasn't even talking to you now.
T2Y in this case actually stands for
Finish the job, Shri.
T2Y actually like for these things stands for talk to you, because of talk to you later. So one thing before I get started with this bit is if you guys first note, oh man, did everything just close out on me?
You're still alive on the stream thing.
Okay, yeah, I think it's still good. So okay, here's the handout. So there's two things that I need to talk about before, like the how for what am I looking at? Where is edit mode? For TTY line edit. This little section here for 3.4. First of all, there's these examples which I'll look at a bit. This is supposed to go into your shell.l. Please do not get started on this until you're confident that you've gotten everything else done. I know it'll be tempting if you're like stuck or something. To like say, screw it, just let me try and get some points from this, and that's fine. But if you're trying to then go back, if you hit a roadblock in this and you say, okay, I'm going to try and go back and work on the other thing I got stuck on, it's going to be really hard to debug if your line editor isn't working and you're trying to debug something else that isn't working. So if you're trying to switch between what you're debugging, don't be afraid to just comment this out when you don't need it. I strongly recommend getting everything else to work first. The number of points that this takes up is not I don't want to actually.
The line editor is 10 out of the 100 points, I believe, right?
Oh yeah,
before it gets scaled.
It's a considerable little chunk, but I would still do it last. Like it's just.
Yeah, I mean like subshell, like the test case for subshell is like already 10 points or something. So yeah. Like wildcarding, I think is more than that. If you're looking at like the test all scripts. So like, yes, this is important if you're trying to get like the 100, but by no means like should you be rushing into this if like you don't have your other stuff complete.
Speaking of, real quick on this lab, if you don't get 100, don't freak out. This is a tough lab, and it's not a horrible blemish on your programming abilities if you can't get it finished in the small time limit that you have.
Especially during the summer semester, yeah. That's a good
Especially
point.
summer semester, yeah.
Yeah, like it. As long as you understand kind of the how, you'll be good for like the exams and whatnot. But to solidify the don't worry if you can't get everything. This will definitely mess with you. This is something that like will be really hard to work with if you don't have everything else working for like testing purposes and stuff. So I really do not recommend moving into this sort of more committal area. There is another portion of code that you'll need to add that I will kind of go through, and I will see about adding it onto the Google Doc request edit access. And that piece of code is in talk2u ramo.c. So I'm not going to explain too much about this. Termios, awesome systems library. This is terminal IO. This is how you handle all of like the TTY attributes and stuff. There's some Termios structs. If you guys have messed with any Linux source or any like pretty low level system stuff, you may have seen this library bouncing around. At any rate, what you will need to do to make sure that when you're testing this, that if you like sometimes what will happen for people is if like they're testing their TTY stuff and they close out their shell and then now they can't type anything, like or rather they can type stuff but it's like all invisible. And just to get that out of the way, what you'll need to do is make like another Termio struct for call it like TTY old, right? So we have our attribute for our shell project, and then we have the old attribute from like Bash or something, right? And we're going to, like here, we're going to get our current IO attributes. Attributes. I put the emphasis on the wrong syllable there. And so this bit is going through and modifying the TTY attribute. Termio struct. We're not going to be modifying the old one that we're saving. Did I just set the same line? Oh my god, you guys should have said something.
Nope.
And then, well, I'll hold on to the last bit here, but the idea is that after you're done, like if you detect a control C or something like that, you want to do TC set attribute 0, TCS and WO. I don't know what this flag stands for. I'm sorry. Normally I'm pretty good about that. And then you just want to do TTY old instead. And so that'll reset our input, because 0 is input, IO attribute to what we had previously before we started messing around with it for our shell project. And so this means that anytime that you close out of your shell, so not Control C. When you do exit, be sure to run TC set attribute here.
On a tangential note, it might make it easier to only have one exit point for your code, especially because you've already gotten rid of Control C for that. So you can totally just put all of exit stuff in a function, and anytime you're doing exit for any reason, which I can't think of a reason why I would exit without typing exit, but who knows. It's good to just have one function that handles exiting, so you can do things like make sure everything gets freed, and also making sure that you do this and change it back to this original TTY mode.
Oh yeah, and one other thing I missed that earlier. It actually shouldn't be a local variable, especially if you're trying to set as an attribute as a Termios attribute later. You want this to be a global thing, so that way you can get it here, sure, and then set it elsewhere in your code. You can make this global. You can make this a part of. You can include like a shell dot h or whatever to get this done. But basic bare bones stuff, you want it as a global thing. here and then use this and then set it later. Or if not as a global thing here, then have it as a shell.h property and then import that include that library. Let me double check actually to see that's how I did it.
Oh, you can't show us your. Don't screen share that.
No, this is just TTY raw mode. So this is even like part of the lab.
Oh,
yeah.
okay, cool.
Yeah. Okay. So I should have checked this beforehand. So I had an old TTY settings. I made it global. I made another function to set the attributes back to what it should be beforehand, and I think I just called this function elsewhere in my code. This isn't mentioned here, and it's literally not mentioned anywhere. So I thought it'd be a good point to make that you can and are free to modify all of these files. If you're not familiar with Termios, this is the bare minimum that you'll need. If you want to mess around with it further, by all means, go for it.
Termios sounds like an Avengers villain.
I'm tempted to look that up. And with that, let me get into how this all actually works. I don't think I need this anymore. Keep it on anyway, so I can talk about these, I guess. So one last little tidbit of like how to actually start working on this. If we go into our examples, hopefully this makes. I think it made. It made the file that we needed, which is this one, I think. So this is just this is gonna run endlessly until like I do something. I'm just gonna type. I'm gonna hit the letter A on my keyboard. It prints a number here. This number corresponds to what the keyboard device actually detects and translates that key press to. Here's B, C, D, A, F, G, H, I. I'm pretty sure these just translate directly to ASCII.
Yep.
Yeah. Here's backspace, delete. Delete printed, what, 3 characters?
4 characters, yeah.
4 characters, yeah. Okay, so these 3 tell you it's like an escape sequence. And this 4th one's like the actual one that you're looking for here. That kind of signifies something. Something along those lines. I'll once we start looking at the tty.c stuff, we'll get to that. Here's like what are we looking for? Arrow keys. Left, right, up, down. Again, you see how they all have this 2791 escape. Note that. Here's Control D. There again, 2791, 66.4. I could pull up an ASCII table right now, but I don't want to. Because I'm afraid of what will happen with Chrome. But yeah, escape character, 2791. Control H, Control A, Control E. Anyway, so that's that. Control C just to get out of there. Let me. Oh. And now to look at readline.c. There we go. So this is where all the code will be going for. Okay. I guess I should look up an ASCII table. All right, you twisted my arm. You talked me into it.
Aha! The plan worked.
Okay, because I'm pretty sure we're gonna need this. So we've got some stuff here. A lot of it will make sense just as you look at the source. Important point here is that you have this readline function. This readline function has a while loop that just reads until a line is done, and a line is done when it hits like enter or something like that. It reads 1 character from your input, which you set up with your Termios attribute there in the other file, checks to see if it's an ASCII character. Again, if you guys do any I/O systems programming, you will see this if statement a lot. If it is just an ASCII character, right? If it's above 32, that means it's printable. Okay, I can't highlight this, thanks. Then you're good to go. There's this line length stuff, line buffer stuff. I'll talk about that. if enter was typed, right, decimal 10, line feed, right, that's return line. You print the new line, you break out of the while one loop there. There's some stuff for control. Here's backspace. We do have one example for the arrow keys so that we don't just leave you in the dark about that. Here's how you handle this sort of escape sequence. Yeah, okay, so 27 is the escape. Is the escape sequence like marker, and then the other, you read 2 characters more for the other information. So it's not always 2791, but 27 followed by something.
You should definitely use that keyboard program to figure out exactly what each number sequence is supposed to be.
Yeah, like if you just have that in another tab and you're writing like, all right, let me just note down what up, left, right is, you can go back and look, right? And you can grab these and just use them. Use that example as a directory. I think that also has a bit about like just detecting and printing out those characters, because there's C files over there. So if you want to look at the source for that executable I was running, you can definitely look at that. Here's how you print backspaces, by like erasing a line. You just write 8, which is backspace, but backspace only moves your cursor left, so it looks like where's my cursor? Hello, there it is. So like backspace does this on your terminal window. That's what it does. Backspace just moves your cursor back. You have to, this is what it's saying, backspace and print a space on top, and then do it again, right? Backspace, print a space on top. And so if you guys are working with the adding an actual backspace or Control D or what have you, be careful of that. You need to manage what's on the line visually, as well as how you're keeping track of it programmatically. And this is about when I'll start talking about the nitty-gritty with stuff like line length. I won't talk too much about history. History is kind of self-explanatory. If you detect an up or down arrow, you look at your history, your history list, which I think is initialized globally here, and you can edit that, add it, reallocate if you need to. You can change these to C++ strings if you want. I think you might need to change some of the makefile, but yeah, I mean you can definitely use like C++ stuff to make your life easier for tracking all of this, because it is annoying otherwise. So this is the stuff that I skipped over before. We have a line buffer that we are tracking programmatically, because what we want is what shows up on the screen that the user has typed to be the exact same as what's in this line buffer array. This is a globally declared thing. I'm not going to scroll up again for it. Okay, you have history length for the array.
Just a quick little warning. I'm a little worried that the video is going to run out of space on my computer because my hard drive's real full. So we might want to wrap this up in the next soon-ish.
Yeah. Oh man, yeah, we've been going for a while. Okay.
Yeah.
You've been going for a while. Don't rope me into this. I was only 20 minutes about.
Okay, I don't know how long I was going, but I felt I was going for a while. Okay, it was the royal we, because obviously I'm an important person. Okay. Anyway, okay. Line buffer. What you want is what displays on the screen to be what the user types in. So you have these variables that keep track of what they've typed in and what's on the the line length and stuff. But keep in mind, this does not, on its own, write stuff to the terminal. That's why you need to do this manually as well. So let me make like another notes thing real quick. No test2.txt. Perfect. So you've got your right, and so this is where you start. This is where the cursor is, and everything's great. So every time that the person types in a visual character, you want to be incrementing the line length variable, and I think that's already done for you. But just be wary of that. You also want to be writing that character to the screen, which is also being done for you. The interesting part comes in when we start throwing in arrow keys. So when you see arrow keys, if you're working on arrow keys, if that's what you're doing, like you will need to start having another variable, not just line length, but also like cursor position or something. So let's say this is cursor position like 0, 1, 2, 3, so on and so forth. So when you type a character, if you type a character here, your line length increases and your cursor position increases. You move your cursor back with the arrow keys. You print the backspace character, right? That just moves your cursor back, doesn't actually overwrite anything. And you decrease your cursor position variable. And then let's say I want to type something in. Then this is going to be some for loop stuff where like, all right, you look at the characters that are left, you move all of them over in your array up by 1, you insert the new character into your array, and then you go in and actually on the screen write out the new characters, right? Because the cursor kind of runs in insert mode. Do I have that button? I do. So like this is what should happen on the screen really fast. So if I hit J, it should be something like this, right? Where you just kind of overwrite the previous characters. That's what will happen using your write commands and stuff. But on the actual like array in the back end, I guess if you want to call it that, you would be managing it by shifting everything over and then leaving room to put in the J there. And this sort of same mentality works backwards for backspace, right? You want to remove that character from the array, shift everything after it over, and then just write everything to the end of the line. That, and then use the backspace character on your cursor to move it back to where the user expects it to be.
That may sound inefficient, but that's only because it is.
Yeah, I mean that is inefficient. That's the only way to do it. That isn't insanely complicated. I also don't want to explain how to do it otherwise, because I also don't remember it like super well. But there are definitely other ways to, like, if you want to do some really fancy stuff with like moving the cursor like manually to specific positions and stuff. But a lot of those are based on the same idea that, like, I mean, at the end of the day, if you're going to be rewriting these specific characters on the terminal, you have to move over there and rewrite them. Like, there's, you can't do anything more than that. Another quick note, if I hit backspace here, just make sure that the cursor position, if it's 0, that if I hit backspace, it doesn't move back. And if I'm over here and I hit right on the arrow key, if the cursor position is at the max, is equal to like the line length or whatever, then you don't want to let the cursor move. Little things like that. The more you work on it, the more it'll make sense. I know that's a TA cop-out, but as Max said, we are running short on time and file space. Use the examples. Make sure you handle this T2Y rod mode stuff. A lot of trial by error. I strongly recommend using a whiteboard or something like this where you keep track of, all right, here's what's happening on the screen, and then here's what's happening in my array. Are those different? Are those the same? They should be the same. How do I handle them, etc., etc. I think with that, that's it for me for wildcarding and TTY. So I'm going to stop sharing.
Good stuff. Okay, so I'm going to just wrap up the very end of this then. So once you get that done, that's pretty much the whole thing. You have that, you have the history. You can do tab completion, which is basically just taking that another level of almost treating it like wildcarding, and just trying to complete based on the file names that are available whenever they hit tab. But that's extra credit. Variable prompt is just letting the user have an environmental variable that's going to determine what the prompt's printout is. Same with on error. Make sure that still works well with the line editor, because if they put in a prompt of a different length, you want to still make sure that it doesn't end up deleting your prompts when you do backspacing. But yeah, that's about it. So whole lab 3 is then due at, I think, 26th, we're saying. Then notice that in the grading, each of the first 2 milestones are only 10%. So those can be important, definitely. Don't forget about actually getting that turned in on time, but it's definitely the most important thing is just that by the end of the whole lab, you have everything working, because that's a whole 70% with the test all. A lot of resources you can use. There's, of course, this on the Lex and Yak stuff that Anthony showed earlier. We have the FAQ and additional note section. They go into a lot of specifics. There's also, I've shown you this for the last lab, but regexer. When you're working with Lex and Yak, the patterns it's using are regex patterns. So this is super, super, super useful just to have access to. Use the man pages. I've shown you a little bit of those on DUP2 and pipe and stuff, but you can get those both through the terminal and on internet. And otherwise, we can take a quick look at the code. This is same skeleton code you got, so it's not going to be anything you can't be seeing. But yeah, here's your shell.l. That's where your Lexer stuff's going to go. Shell.y. Those are both going to be converted to C programs at some point. Simple command is where a lot of the stuff is going to go. It's just about each specific simple command, not including redirects and everything. Just one command that is piped, basically. Catgrep. Here's a good example of a program and using pipes. So I won't go through it step by step, but it's combining cat and grep into one program using pipes. I would look at this before you really get started with much, just because you can figure out how DUP2 works, you can figure out how exec works. In this case it's exec LP, but exec VP is fine as well. Learn how pipes work. Here's the control C one. This is good because we can use it to see how we can get rid of control C and teach it to ignore it, including using sig action and creating the sig action construct or struct there. Here's regular expressions in C. So you might want to have regular, specifically in wildcarding, you're going to want to use regular expressions that aren't in Lex or Yak. For those, you're going to want to use these. You're going to want to use C's version of this. Basic idea with that is you have, where is it? You take your regex, which is going to be this RE, which I believe is a, where do we define it? Actually, there it is. Regex T-type. You're going to compile it with the string that represents it, and then you're going to use a reg match to match it to things. Regexec is going to run that and store the result in the match. You have access to all these files, by the way, so make sure to check those to see how they work. Simple command.hh, that's fine. We looked at this. Sri showed you that. This is where this command execute, this is where a good portion of the shell is done. This is going to be actually executing your commands that you have. At first, what it's doing right now at the start is it's just going to print prompts, and then it can print this nice table that we have here that we're going to use for making sure that our parser is correct. But eventually you're going to get rid of that and instead replace it with using fork and exec VP and all of that. Command.hh, that defines the command struct. Notice that we have room to store our out file, in file, air file, and whether it's going to be a background process or not, depending on if it's an ampersand or not. Shell.cc, you won't have to touch this, I think. This is just starting off the shell by throwing out a prompt and then doing YY parse. And read line, which we also went over. So that's it for this video, I think. Any closing statements, guys?
No, nothing else comes to mind.
Nothing here except make sure you guys start early.
Oh yeah, if you're, there were some people who started Lab 1 way too late, and it did not go well for their grades. This is double that. If you start this one late, you're not going to be able to finish it because Shell doesn't have a lot of super difficult concepts, but it has a lot of code that you're going to have to write, and it's very bug prone, and you might end up having to do stuff over or relook at things, and it's a very interesting, very cool lab because it's kind of the midpoint of CS, I've always called it, of Purdue CS anyways. But it's, start early. Start early.
Start early and use examples often. Whiteboard out like problems that you're having. Think about what data is actually contained in like each string and stuff like that. Don't just kind of assume that everything that you've written is working, and then be surprised when it all does come together, right?
Yeah.
Test each individual step, use print statements, GDB.
Use GDB a lot. I did a whole video on how to use GDB, and I might do a mini one later because there's things in GDB that you can do. Like you can go pick whether you go into the child or process or the parent process with GDB, but we'll talk about that another time.
Alright, sounds good. Felt great to be finally included in the channel along with Shri.
Yeah, we're this is the best channel on YouTube.
I'm
Yay.
officially YouTube famous. This is my career accomplishment.
Yeah, and it's you're also officially sketchy because it's Max's sketchy videos.
Oh man, feels great.
Yeah.
If my code wasn't sketchy already, it sure is now.
Sure is.
I think I should be the one saying that. No one ever needs to look at my implementation of Shell. No one ever does.
Gosh.
You see, they think
whatever you do.
You think that TAs don't
Whatever
show you their code because we're like not allowed to. The real reason's that it's all horrible.
You should not forego learning Lex and Yak just to put it all inside of command.cc. And when I say all, that's not much of an exaggeration. That's not much of an exaggeration.
I don't think that's not an exaggeration at all.
Aside from tokenization and syntax,
but the redemption is real. The redemption is real, though. You made the Lex and Yak slides.
Yeah.
No. It was fine. It just wasn't fine.
Well, with that beautiful.
I see what you mean.
With that beautiful full circle moment.
You hated Lex and Yak, and then you came back as a champion.
And now you teach Lex and Yak.
Yeah, it's an odd one. Now that I think about it, the only words of advice I can give is if there's some points that you just can't get, like my shell could not handle new lines well, and so I wouldn't pass test robustness, just do extra credit instead to make back the points. That's a possibility.
Yep.
Oh, yeah. There's a lot of cool extra credit that's out there. I feel like if we talk about the extra credit that we did, like a lot of the impressiveness for this stuff, like the points that you get is like figuring out that this is something that you can do. One example that I'll give is like there's a shell level environment variable that is like, you can check this on your bash or whatever. And so I know that when I was implementing my shell, that whenever it ran, it would get that environment variable and then add one to it. So if you ran it from bash, you would be at shell level 2. And if you ran it again inside of it, it would be shell. Like that's the way that bash itself does it. But like that's something that I don't know how I knew that. I don't know where I knew that from, but I happen to know, and I got like 1 point for it. So like there's all sorts of things that you can do to like make your specific shell implementation just a bit.
Don't go too overboard, though. We definitely don't want you not doing the whole lab, but then saying, hey, I made a text editor instead for extra credit. Like, that'd be cool, but we're not giving you much extra credit for that.
Yeah. Like, I mean, and on the real, like, my little example there, I need to have environment variables done. to do like, if you want to do like some crazy cool like subshell stuff, you need to have subshell done first. So a lot of the extra credit like does actually require you to have that part of it done.
Yeah.
Just saying.
Oh my gosh, here's another example of Shree talking twice as much as the rest of us. Alright.
All
This is rare. This is
I
rare.
was really
video
hoping
won't
I was really hoping that you were just gonna keep going so I could cut you off with that.
Shut up.
I was like, try it, just try it.
All right,
Might
end
work.
of the video. Do. End of the video. Bye.
Outro jingle.
Bye. End of the video.
Ba-da-ba-ba-ba-ba.
Woo.